Welcome back. So in previous lecture we talked about the active faults, what are different type, why, in what way we define the active fault. So let us see a couple of examples of that, but before going to the particularly the active fault part, let us see what we have, how we can classify the different faults. Okay. Now fault slip is mostly we have taken in response of the stresses, either they are in extensional, compressional or lateral shear. Okay. In almost all geological situations, stresses are mainly we take they are mutually perpendicular to one another. So if you are having like sigma 1, sigma 2 in this fashion, okay, then you will have a reverse faulting, and this is mostly seen in the areas where we are having compression tectonic environment. And if you are having the sigma 1 which is at the top and the least along the fault plane, then we will have the normal faulting. This is in the extensional tectonic environment. And then if you are having an oblique, okay, then we will have the strike-slip faulting environment. So mostly this is we see where in Himalayas also we have this type of faulting which has been seen. Like one of the largest fault system we are having of strike slip motion is Karakoram fault. So we based on the differential stresses, how they are acting upon, and mostly based on the sigma 1, we can classify the different type of faults, whether it is a reverse fault or a normal fault or a strike slip fault. Then style of deformation, if we take in general, okay, then what we have is that if we are having the extensional tectonic environment, then we will see the normal faulting, and mostly what you will be able to see is the thinning up of the crust. Okay. So we are thinning up the crust over here. But if you are having the shortening, okay, so this was the stretching here, but if you are having shortening in the compressional tectonic environment here, so we will mostly have the folding here, okay, and we are looking at the shortening of the areas, okay. And finally, what we see is the displacement in terms of the reverse faults or the thrust faults. And if we are having shearing, okay, so we are twisting the area, okay, then we will have mostly initially we will see the bending, and then we will have the strike slip motion. Okay. So the motion will be along the strike slip. Now if we are having the combination of both this folding, shearing, then we will have dip slip folding. Okay. So dip slip folding can be either like oblique slip, what we call. So we will have reverse component and strike slip component, or we will have the normal component and the strike slip component. So both we can have in combination, which can occur. Now this is one of the very famous example of the fault scarp from California, okay, where you can see the fault scarp over here. Okay. This is the surface expression of the faulting which took place in California. And if you know this location, like that is what I was talking about and emphasizing most of the time, that if you know the location, then you will avoid putting your structures on this, okay, because this will displace, and this is what we call the active fault. Okay. So this fault or the area will be displaced during next earthquake. So this is what we call the faults marked on the surface, or the manifestation of the crustal deformation on the surface. Now in this cartoon, which clearly shows that one block has moved past each other in a particular direction. Okay. So I will just put again, if you see this, so this block has moved in this direction, whereas this block is moving here. Okay. So this is the strike of the fault. So it has moved along the strike of the fault, hence it is termed as the strike slip fault. And if you stay, like if you are having a strike here, okay, and if you are staying and you are viewing the area from this place, okay, then this is your right and this is your left. Okay. So, if this block has moved like this and this has gone like that, okay, so the block moving towards you, based on that you will term this fault as an right lateral strike slip fault. So, this is what we can classify, and if it is opposite, then we will say. This is irrespective of where you are standing, either you are standing on this side or you are standing on this side, this will be the same actually. So, this is an example of a right lateral strike slip fault. Another one. Okay. Now, this shows the movement along the dip. Okay. So, this is your strike you are having. So, this is your dip direction. So, along the dip the movement occurred. So, this is our dip slip fault, and since the hanging wall, this is hanging wall, this is what we call the foot wall, this will remain stationary. Okay. So, this will be the stationary wall, this will be the wall which will move, this hanging wall. Okay. So, hanging wall has moved down. Okay. Hence, we term this as a normal fault. And if the hanging wall has moved up, so in this case this is the foot wall and this is your hanging wall. Hanging wall has moved up. So, if the hanging wall is moving up with respect to the foot wall, then we term that as a reverse fault. And if we consider the angle, depending on that you can classify it whether it is a reverse fault or reverse fault, or you can say it is a thrust fault. Sorry. So, based on this you can classify whether it is. So, this is if it is less than 45 degrees and this is greater than 45 degrees. Now, here there is an interesting thing. What you see is that at the lower part there is a displacement, but in the upper part we have deformation. Okay. So, what we can say that this is like there is a folding here of this layer. This layer just got folded, but this layer got displaced. Okay. So, there is a displacement over here, but there is just a folding. Okay. And no displacement has been seen on the surface, just we see what we call the warping on ground. Such type of faults or the displacements are termed as, since this again we have to say that, look at this part, that this is a hanging wall and this is our foot wall. Okay. So, based on this we can say that this is an angle is probably a low. So, we say this is a thrust fault, and since there is no displacement on the surface, we term this as an blind thrust. Okay. So, in other way I usually say that the rupture has not seen the surface. Okay. Hence, we say this is a blind thrust. Another combination which I was talking about. So, what we have here on your right hand side, we are having a block which has moved in this direction and which has also moved like that. Okay. So, we have the two components here. Okay. We have the component along the strike, we have the component along the dip also. So, we call this as a dip strike and dip slip faults, but in other terms we call this as an oblique slip fault. Okay. Here also we are having the movement which has occurred is like this, and then movement which has occurred is along the strike also. So, this block has moved down, this is your hanging wall, this is your foot wall, this is your hanging wall, this is your foot wall. So, this is having the strike slip as well as you are having the reverse component. Okay. Here you are having strike slip as well as you are having normal component. Okay. So, in general we call this as an oblique slip faults. Okay. Now, coming to the earthquakes, we all understand that the earthquake is a sudden release of the stored energy within the earth crust. Okay. So, what we have experienced over the past, now earthquakes mostly will result into strong ground shaking, and ground shaking will result into the damage to the buildings. Okay. So, people mostly get affected because of the pattern of construction and all that. So, this is a part of what the civil engineers should take into consideration by understanding that where the earthquake is likely to occur, they should know, and what will be the magnitude of that. Okay. Based on that, definitely they will design the structures following the building codes and all that. Here are a few examples from 1994. This is from Los Angeles earthquake damage pattern. Not many houses were been collapsed. This from 1995 Mexico City earthquake, huge damage. This is from 1995 Kobe earthquake. Okay. Now, here one interesting thing what they have done is that they preserved the surface rupture. Okay. And this photograph, it shows the museum of fault rupture. So, they have preserved the fault rupture, and this is the way how they have created a venue to have this public awareness. Okay. So, people now like tourists go there and then try to see that what exactly happened and how the earth moved. Okay. And what are the signatures of such movement over the time. So, this again the magnitude was above 7, and this was one of the devastating event in Japan. This is from 2001 Bhuj earthquake. Many villages experienced total damage. Okay. So, when we say total damage, that means all the houses in that region or in that town got damaged or they were razed to the ground. Okay. 2005 Kashmir earthquake experienced huge damage, not only in the part of the Pakistan side, but in the Kashmir side also. Okay. Now, this is one interesting part which usually I talk about. Now, 2005 Muzaffarabad earthquake occurred along a known fault, okay, which was termed or named as Thanda fault. This was identified long back by a Japanese researcher, and he is my teacher also. He identified this fault in 1999. He informed the Geological Survey of Pakistan that this fault is likely to slip in future, and this is one of the active fault in this region. Okay. But the geologist did not pay much attention on it, and it was been experienced in 2005. So, this was on the known fault. And what you see in this photograph here, okay, you have a scarp here. This is what we call this fault scarp. So, if I put a sketch here, it looks like something like this. Okay. So, this is a scarp which is quite high. Okay. That means that this scarp was not developed just because of the recent 2005 event. This shows the cumulative, that is what we call the cumulative scarp. Okay. So, it has the acquired the displacement over the time. Okay. So, it is a multiple event scarp. Okay. It's a multiple event scarp. And if you carefully look at what happened here. Okay. So, fault line, if you have to draw, I will put the fault line over here. Okay. It passes through this area here, and this is a type of a reverse fault or the thrust fault. Okay. So, the buildings which were been sitting on the scarp were been raised to ground. Okay. So, this all squarish part which you see, okay, are the top of the or the roof of the houses. Okay. They were raised to ground, whereas this survived, nothing happened to this. Okay. So, this is your footwall and this is your hanging wall. So, hanging wall moved. So, if I put the fault here, then this is something like this. Okay. So, this moved. Okay. So, this is your hanging wall and this is your footwall. So, more ground acceleration will be observed on the hanging wall side as compared to the footwall side. So, this is one of the best example which we should learn from. This is a lesson which has been taught to us, that we should not ignore any active fault if it has been identified, and that what we are doing in India, we are trying to identify this type of active faults, from which location it is passing through and what is the history or the background of that active fault in the region. Okay. Now, understanding earthquake efforts to minimize the hazard and risk. Okay. So, what best we can do to minimize the hazard and risk? Assessment of earthquake hazard at a particular site includes identification of one, the tectonic framework. So, regional tectonic framework has to be identified, that what will be the pattern of the regional, whether it is in a compressional tectonic environment, whether it is an extensional or it is having the oblique deformation going on. So, that we have to take into consideration. Okay. So, based on, for example, in Himalayas, we have to look at that what is the pattern of deformation, it is in compressional tectonic environment. Okay. That we need to understand. Then based on that, we can talk about the geometry of faulting. So, we need to know that what is the geometry of faulting, whether it is a normal fault, is a reverse fault or a thrust fault or a Strikeslip fault. Then Shepsel pattern of the fault. Okay. Whether the pattern of the fault changes along the strike or it remains the same. Then seismic source. Okay. How deep the earthquake will occur in that region, it will be shallow or deep earthquakes. What will be the magnitude of an earthquake if any earthquake along the particular fault to take place. Okay. And then what is the recurrence interval. So, this all information, if you have, you will be able to reduce or minimize, we can say, okay, the hazard and risk posed by such mega earthquakes or large magnitude earthquakes in seismically active regions. Okay. So, in short, what ultimately we aim to, okay, we are extremely bothered about that what will happen to the urban cities. Okay. But in India we talk about that what will happen to Delhi. Okay. But it is not just Delhi. There are many cities which are sitting close to the foothill zones of Himalayas, which will be affected if we are going to have a large magnitude earthquake in near future. So, this is extremely important for us to understand. Now, in short, like why what we are interested in, we want to know that what is the local condition of the specific site or the urban site, how far it is sitting from the fault. If the fault is over here, then how far it is sitting. Okay. What is the distance between this fault and all that. Okay. How deep will be the earthquake? So, same what we talked in the previous one, that we need to know the tectonic framework. Okay. We need to know the focal mechanism, what type of faulting will take place. we need to know how much energy will be released, because this is extremely important to understand, and this depends on the magnitude of an earthquake. Okay. And then seismic wave radiation and propagation. So, if you have the fault or the source of the earthquake sitting in different area, like for example, we are having the settlement here and then earthquake source is here, then the waves will propagate in this direction. Okay. If in the earthquake wave or the settlement is this will. So, we need to know that what will be the radiation and the propagation of the seismic waves, influence of local soil conditions. Okay. This we talked in the previous course, because this will amplify the seismic waves traveling through different type of material. Okay. So, if you are having softer and sandy material, then we will have the more amplification in that area. So, for example, if we say that this is the Indo-Gangetic plain, then we should be bothered about it. Okay. So, this part should bother us, because this will have more amplification of the seismic waves. Earthquake hazard assessment by predicting models and earthquake ground motion. This is again is related to the seismic wave propagation. Okay. So, we are mostly interested in knowing that what will be the magnitude, how far we are sitting from the fault, active fault. Okay. Now, about the recurrence interval, if we look at about the earthquake recurrence interval, it has been understood that it depends on the strength of the rock and all that. Okay. But whether this is correct, if both we have been talking about that over the time the strain will develop if we keep on building up the stress. Okay. Now, if we keep on building up the stress at a particular threshold point, the rock will rupture or the crust will rupture. Again, to trigger the similar magnitude earthquake, you will require this much of time. Okay. So, again the strain will build up and then there will be another rupture. If this very systematic pattern is been repeated, okay, then we can easily predict the earthquake. Okay. So, for example, we can talk about the recurrence interval. Okay. So, if this was the amount of the time which was been taken to acquire the strain to slip here, then what will be the next here. Okay. So, this time we will have another earthquake. So, this is one point which we keep on talking about, that if we are having very systematic earthquake pattern or the repetition, then we will have the next earthquake which can be predicted. Okay. But this never happens, okay, because sometime we have the major earthquakes which have occurred here, and in between we may have a moderate magnitude earthquake. Okay. Now, this moderate magnitude earthquake will lead to incomplete release of this strain, which can very quickly trigger another event. Okay. It could be in large magnitude, and this whole thing is dependent on the change in the strength of the rock. So, if you change, because over the time the strength of the rock will change, because of that you may not have a very systematic earthquake occurrences. Okay. The repetition or the time which has been taken, the recurrence will change, okay, and that what we have experienced in Himalayas also. But then also I would say that if we do the studies in a proper way, we will be able to identify the locations of the active fault, and we will be able to at least say that this will be the magnitude of an earthquake which is expected on that particular fault. So, this is an advantage of what we are doing, identification of active fault and mapping. Okay. So, change in the stress from earthquake on the nearby can also trigger the earthquake in that area. Okay. So, if we are having an earthquake on the another nearby fault, can also result or trigger the earthquake on the fault, which was not going to trigger an earthquake very quickly in the recent time. Okay. This is what we call the triggering earthquake or triggering stress. Sorry. So the stress has resulted into the increase in the possibility of occurring an earthquake in the adjacent fault. Okay. This is what usually we'll expect. Okay, if there is a change in the rock strength and all that. Okay. So finally, what is important for us and why we are trying to understand and know the location of the active faults. As I told that we are interested that how far we are sitting from the fault, okay, how deep it will occur. Okay, fine. That is one point, and what will be the magnitude of these events. Okay. So for example, here we are giving two scenarios. Okay, one is like 615, okay, which is sitting away, that this fault can trigger the magnitude of 6.5. Okay, whereas this earthquake is away, but it will slip, okay, with a larger amount. Okay. Now in this slide, there is that what we have been talking about, that we are interested in knowing that what is the location of the fault. Okay. So here they are marked two faults. This is one and this one is another one, okay, on the surface, and how much far they are located, and for example, if we take the epicenter, then how far they are located from each other. Okay. So one is like MW7. So this fault is capable of triggering consistent with the rupture of 50 kilometers, and the slip will be 2 meters, whereas here there will be less slip, okay, which is around 30 kilometers. Okay. Now the most important part which we require from for the settlements around the area or the site specific studies, okay, we require that what will be the intensity of the shaking in that particular region. Okay. Now if you see this picture here, okay, this shows that there are no same colors everywhere, but most of the proportion is having this one. Okay. So that depends on that this areas will have low intensity if the earthquake is triggered, and if you're having the epicenter right sitting over here, okay, then the red areas will have the higher intensities. Now this depends on that what is the lithology or the geology of this area. So that will vary from place to place, and that what we call is extremely important to have is the seismic zonation map, micro seismic zonation map, not on the regional scale but on the micro scales, okay, of different areas. Okay. So this is what ultimately is required. So how far is the fault from the city, and on what type of material the buildings are been standing, that is extremely important. Okay. Now coming to the Indian part, okay, we have I would say that we are not left out from any side. Okay. So we have if we start from the south, we have Andaman and Nicobar here, which experienced several earthquakes of magnitude 7.5 and greater, okay, in 1679, then 1762, 1849, 1881, 1941, and then we are having finally the mega one was 2004. Okay. So this is the area of subduction zone and Sumatra Andaman subduction zone. Coming to the Assam side, we have the large the magnitude earthquake was 1950, and then coming to this area, this whole area is the extremely active region. Okay. And then on the western side, we are having the Makran subduction zone. Okay. So this whole area of the Indian subcontinent, there is a coastline, okay, because we have extensive coastline. This coastline is vulnerable to not only the earthquake shaking, but also from the tsunamis, which will be triggered from the subduction zones on the eastern side and the subduction zone on the western side. Whereas this region is extremely prone to the large magnitude earthquake, that is the Himalayan zone. Okay. So, we are having the collision which is going on over here along this boundary. Okay. Over here the Indian plate is subducting or colliding with the Eurasian plate, okay. And we have couple of earthquakes listed over here. Okay. So, we have 1885, 1555, 1905, 1934, 1950, 2005. Okay. And I have not added here more is the 2015 Kodari earthquake. Okay. So, we are having another one in Nepal which was 7.8 or so. Okay. So, we have another events from this region also. Okay. So, this shows that this area is extremely active. Along with that, we have the region of Kutch, which is again and one of the most active region in the stable continental region, because we consider that this part of the India falls under the stable continental region. Okay. So, if this is there, then even we are having very large magnitude earthquakes from this area. Okay. Now, question is whether we should consider this Kutch as an stable continental region, or we will start discussing this part further in the next lecture. Thank you so much.